32 earthquakes struck one small patch of Northern California in a single day this week. Stretch that window to 7 days, and the count climbs to around 80. The strongest was a magnitude 4.2. Every single one of them is shallow. Every single one is roughly 75 miles from downtown San Francisco. And here's the part that has seismologists leaning in close to their screens. The sequence is crawling across the landscape in a direction that matches no known fault in the region. It's moving the wrong way. And the strangest thing of all is that scientists have watched this exact fault behave this exact way before, and they know what it turned out to be. If you stay with me to the end, you'll understand what's really happening beneath that ground, and I'll give you the one single number that would change this entire story overnight. If you find yourself hooked by the way the Earth actually works, do yourself a favor and subscribe right now, because this is the kind of story that keeps developing, and you'll want to be here for the next chapter. Let's start with exactly where this is happening, because the location is half the story. There's a stretch of hill country in northern Sonoma County, about 8 kilometers east-southeast of a small town called Cloverdale, that has generated somewhere around 80 earthquakes over the past week. 32 of those arrived, inside one 24-hour stretch, ending on Saturday. The biggest of the whole week hit magnitude 4.2, and a magnitude 3.8 rolled through just after midnight on Saturday morning. All of this is unfolding at a depth of only about 2 to 3 miles beneath the surface, with some of the tremors even shallower than that. To put that location into terms that actually mean something, we're talking about roughly 75 miles north of San Francisco. This is wine country, just off Highway 101, in rolling terrain where the nearest town has a population of only about 9,000 people. Cloverdale has felt plenty of this shaking, and so have good chunks of Sonoma and Mendocino counties. Now, here's the first twist, and it's an important one. None of these earthquakes has done any real damage. A magnitude 4.2 is a solid, get-your-attention jolt, but it's not a catastrophe. A 3.8 rattles the dishes in your cabinet and maybe knocks a picture crooked. If you judge this whole sequence purely by the size of the individual quakes, you'd shrug, file it under ordinary Northern California background noise, and move on with your day. And that's exactly why what I'm about to explain matters so much, because the danger, or the mystery, isn't in the size of these quakes at all. It's in their behavior. So let's clear up a word you're going to hear over and over: swarm. Because a swarm is not just a fancy way of saying a lot of earthquakes. It means something very specific, and once you understand it, everything else clicks into place. A normal earthquake sequence has a shape to it, a signature you can practically draw on paper. One big event dominates everything. Scientists call it the main shock. Then everything that follows is smaller, it comes afterward, and it fades away along a predictable decline that seismologists have been mathematically fitting to real data since the 1890s. You can literally watch it happen after any large quake. The big one hits, the aftershocks pile up thick in the first few hours, and then the rate of shaking drops off steadily, hour after hour, like an echo dying out. A swarm does none of that. There's no single dominant quake, there's no clean fade out, and often there's no obvious starting gun either. Instead, the energy gets spread across dozens or even hundreds of similarly sized earthquakes, playing out over days or weeks. And a swarm can go completely silent for a full day and then, for no visible reason, roar back to life. That behavior is a fingerprint, and it points to a completely different cause. It's not one locked up patch of fault suddenly snapping and then settling down. It's something moving through the rock, switching on one small structure after another, like a hand flipping a row of light switches down a hallway. And that is precisely why the people watching this earthquake catalog in real time are watching it so intently. But again, it has nothing to do with how big the quakes are. It has everything to do with the direction they're traveling. So let me ask you something before we go deeper, and I genuinely want your answer in the comments. When you hear that the ground is shaking 80 times in a week just 75 miles from a major city, is your first instinct fear or curiosity? Drop a comment and tell me, because I think the honest answer says a lot about how we relate to the ground under our feet. Here's the geometry problem. The faults in this part of California all run the same way. They're all part of the Great San Andreas system, so they share its orientation, running roughly from the northwest down to the southeast, which on a map looks more or less like a north to south line. The Maacama fault, which is the structure this swarm is sitting on or right beside, is what's called a right-lateral strike-slip fault, and it follows exactly that same trend. It runs north from Santa Rosa, up past Ukiah, and it forms the northern continuation of the Hayward and Rodgers Creek fault system. Hold on to that connection, because it comes back later in a way that matters. Now, when a fault like this produces an ordinary aftershock sequence, the earthquakes line up along the fault itself. They form a long, stretched-out cloud that traces the exact plane of rock that broke. That's not a loose guideline. That's simply what a fault rupture is. The earthquakes mark the edges of the slab that slipped. But the Cloverdale sequence is not doing that. It's spreading from west to east. It's running across the grain of every mapped fault in the area, cutting at a steep angle across the very structures it's supposedly happening on. The people tracking this catalog hour by hour describe it as spreading out in an abnormal way, running opposite to how the faults themselves run. And the blunt conclusion they've drawn is this. It is not an aftershock sequence. They are absolutely right about the observation. The geometry genuinely is strange, and it's the single most important fact in this entire story. But here's what makes this so much more interesting than the doom scroll theories floating around online right now. There's a published, peer-reviewed explanation for exactly this behavior on exactly this fault. We'll get there, because it's both more fascinating and far more grounded than the alternatives. But first, let's be honest about how little we actually know about the fault this is happening on. The Makama fault moves at about 9 millimeters a year. That's roughly a third of an inch annually, which is a meaningful rate for a California fault, comparable to some of the more famous structures in the Bay Area. And parts of it also creep. That means sections of it slide along quietly, continuously, without producing earthquakes at all, at something like 7 millimeters a year. That creep number deserves a real pause because it changes how you should read everything else. A fault that creeps is a fault that's releasing its built-up stress a little at a time continuously, without violent snaps. The two sides of the rock slide past each other slowly enough that over decades you can actually watch it bend a curb or offset a fence line. Faults that creep along their entire length are generally considered less dangerous because the strain never piles up to the breaking point. But faults that creep in some spots and lock up in others are a very different kind of problem. The locked patches keep loading with stress while the creeping sections quietly slip past, and the boundary between the two is exactly where things tend to break. On the Maacama, we know creep is happening. What we don't have is a good map of where that creep stops and the locking begins. And here's the part that should really get your attention. Scientists know remarkably little about the Makama fault's earthquake history. Its paleoseismic record, which is the trenching and sediment work that tells researchers how often a fault has unleashed big earthquakes in the deep past, is thin. Its earthquake cycle is poorly understood. Nobody can tell you with real confidence how often this fault produces a major event, because nobody has been able to pin down the pattern. And that uncertainty matters because the Maacama is not some isolated crack in the ground. Follow it south and it connects to the Rodgers Creek fault. Follow Rodgers Creek south and it runs right under San Pablo Bay, where researchers have confirmed it links directly to the Hayward fault. The two are now mapped as one single continuous structure rather than two separate faults. So think about what that means. The thing shaking under Cloverdale this week sits at the northern end of a chain that runs straight down into the most densely populated part of Northern California. Now, I want to be very careful and very honest here, because this is exactly where people talk themselves into panic. This is not a prediction. The Maacama producing 80 small earthquakes does not mean the Hayward fault is about to do anything at all. Faults in a system are not dominoes lined up to knock each other over. Treating them that way is precisely how people conjure up forecasts of disaster that never actually arrive. But the structural connection itself is real. It's mapped. It's not in doubt. And it's the reason this particular fault gets far more attention than its modest size alone would ever justify. Now let me take you back in time, because this is where the mystery cracks wide open. In August of 2020, an earthquake sequence kicked off inside the Makama fault zone. It reached a maximum magnitude of 4.2. It generally faded over time, but it kept restarting, flaring up again and again, persisting on and off all the way into December of that year. And when seismologists first looked at it, it appeared every bit as bizarre as the current sequence appears now. Same wrong-way geometry, same refusal to behave. 3 researchers spent the years that followed taking that 2020 sequence completely apart. They published their findings in a respected geophysics journal in 2023, under a title that basically gives away the ending: fracture mesh faulting in the swarm-like 2020 Makama sequence. What they did was brute force precision science. They used a technique called waveform correlation to detect earthquakes far too tiny to show up in the standard catalog. And they relocated all of them relative to each other with extreme precision. Then they calculated high-resolution focal mechanisms, which are the solutions that reveal the exact orientation of the fault plane that produced each individual quake. When they were done, they had relocated 3,520 earthquakes, most of them smaller than magnitude 1, quakes so faint that nobody standing directly above them would have felt a thing. And here's why that method is everything. The small earthquakes carry the information. A standard regional catalog might record only a few hundred events from a sequence like this, everything above roughly magnitude 1.5, and it can only locate them to within a kilometer or so. That's enough to tell you where the sequence is, and almost nothing about how it's built. But push that detection threshold down below magnitude 1, relocate every tiny quake relative to every other one, and suddenly the blurry smear resolves into sharp individual planes. You stop seeing a fuzzy cloud and you start seeing the actual faults. 3,500 events is the difference between knowing that something happened and knowing what happened. And what that catalog revealed was this. The sequence did start on a right-lateral fault, plausibly a strand of the Maacama itself, behaving the way the Makama is supposed to behave. But it didn't stay there. It went on to activate a whole population of secondary faults running the opposite direction, left lateral structures, arranged in an overlapping, stepped staircase-like pattern, cutting across the parent fault at an angle. Together, the main strand and all those cross-cutting secondary faults form what the authors named a fracture mesh. Not one clean plane, but a three-dimensional interlocking network of small faults, every one of them capable of slipping, every one of them oriented a little differently from its neighbors. And that is exactly why the geometry looks wrong. A fracture mesh doesn't produce a neat, stretched-out cloud along the main fault because the earthquakes aren't happening on the main fault. They're happening on the cross structures, which, by definition, slice across the regional grain at a high angle. A sequence spreading from west to east across a north-south fault system isn't behaving impossibly. It's behaving exactly like a fracture mesh, a thing this very fault zone demonstrably produced 6 years ago, at the same maximum magnitude of 4.2. Let that sink in. The same fault, the same weird direction, the same ceiling of 4.2. We've seen this movie before. But there's a second half to that discovery, and it's the part that explains why any of this is happening in the first place. Fracture meshes are tied to fluids. The authors say so directly. These interlocking networks match what's been found elsewhere in cases of fluid-driven faulting in earthquake swarms. And the mechanism, once you see it, is beautifully simple. Deep underground, rock is squeezed shut by the crushing weight of everything above it. Now push pressurized fluid, water, gas, whatever, into that rock, and you reduce the effective stress that's clamping the faults closed. Faults that were locked tight suddenly become slippable. And because that fluid is seeping through a whole damaged volume of rock rather than gliding along one clean surface, you get many small earthquakes on many small structures spread over days and weeks, instead of one enormous earthquake on one big fault in a matter of seconds. That is the textbook definition of a swarm, and it fits what we're seeing almost perfectly. No main shock. A magnitude 4.2 leading a crowd of 80 rather than a magnitude 5, with everything neatly decaying away from it. A sequence that stubbornly persisted for a week and then re-intensified rather than fading out. And that magnitude, 3.8, arriving after midnight on day 6, which is simply not how aftershock decay is supposed to work. The regional setting backs this up too. This part of California sits near the Clear Lake volcanic field, inside a broader hot zone that hosts the geysers, the largest geothermal electricity complex on the entire planet. The crust here is warm, chemically active, and structurally beaten up. It's precisely the kind of place that keeps fluids circulating at depth. And I want to be crystal clear about one thing because it comes up every single time. The swarm's epicenters are in a separate area from the geothermal production field itself. This is not a story about humans accidentally triggering earthquakes by pumping fluid. This is regional geology, natural fluids, and naturally fractured rock, in a place that has been doing this entirely on its own for a very, very long time. But here's the honest caveat that matters more than anything I've said so far. That 2020 analysis took years of high-precision, painstaking post-processing on thousands of relocated micro-earthquakes. Nobody has done that work on the current sequence, because the current sequence is only about 6 days old. So the fracture mesh is the best supported explanation available right now, but it is not yet a proven finding. It's the hypothesis that fits best, held loosely until someone does the math. Now here's something that reframes this whole thing, because this swarm did not appear out of nowhere. On June 24th of this year, a magnitude 5.6 struck near Ukiah on the same fault system. And that was the largest earthquake ever instrumentally recorded on the Makama. Not the largest in a decade. The largest since instruments have been watching it at all. That June event deserves far more weight than it got at the time. But here's the crucial, level-headed way to read it. When a fault produces the biggest earthquake in its instrumental record, the honest interpretation is not that the fault has suddenly become more dangerous. It's that our record is short. Instruments have only been watching the Makama for a few decades. The fault has been moving for millions of years. A record-setting 5.6 tells you far more about how brief our observation window is than about the actual state of the fault. But it does establish one useful, concrete fact. This system is capable of producing events in the mid-5 range. It did exactly that 6 weeks ago, about 40 miles north of where the current swarm sits. Then, on July 28th, a magnitude 4.3 hit near Cloverdale at around 8 in the evening Pacific time, at a depth of roughly 5 to 12 kilometers. The U.S. Geological Survey flagged it as a potential main shock, and the sequence that followed ran to more than 160 events. And now this week, we've got 80 more earthquakes, another 4.2, and a geometry that refuses to line up with the fault. So the correct framing isn't that a swarm started last week. The correct framing is that the Maacama fault system has been switching itself on and off for 6 straight weeks, growing more complex each time. And it has not stopped. Whatever is driving it, and the fluid explanation is by far the strongest candidate. It has been driving it since late June. That's the primary story. Everything else I'm about to tell you is context. And it's the reason so many people started nervously staring at Northern California in the first place. Because on Friday night at 49 minutes past 9 Pacific time, a magnitude 5.6 earthquake struck beneath the ocean floor west of Vancouver Island, British Columbia, about 600 miles up the coast. The depth was around 10 kilometers. Light to moderate shaking was felt across Vancouver Island, with reports coming in from as far south as Washington State. No damage and no tsunami threat from any agency. And as of the following afternoon, more than 12 hours later, not a single aftershock had been catalogued from it. That silence is worth flagging. Part of it is just detection limits, since a quake below about magnitude 4.5, sitting 200 kilometers offshore, won't even register on land-based instruments. But a genuinely quiet spell after a 5.6 on an oceanic fault is still a data point, and it's the exact opposite of what the Cloverdale sequence is doing. And here's the detail that really made people sit up. This was the second magnitude 5.6 on that exact same structure in just 12 days. An identical-sized event had struck the same region on July 20th, located about 219 kilometers southwest of Port Hardy, at essentially the same depth, felt as far away as Metro Vancouver, more than 450 kilometers off. 2 earthquakes, same magnitude, same depth, same structure, 12 days apart. That sounds ominous until you understand what's actually happening up there, and once you do, it stops being scary and becomes genuinely fascinating. What most people casually call the Juan de Fuca plate is actually 3 plates. The Gorda plate sits at the southern end, offshore of Northern California. The Juan de Fuca plate proper is the large middle section, and the Explorer plate is a small fragment at the far northern end, west of northern Vancouver Island. And that Explorer plate is being torn off. It's fragmenting along its boundary, and the working interpretation among researchers is that it's slowly decoupling from the subduction process entirely, that on geological timescales, it may stop diving under North America altogether and convert into a sliding transform boundary instead. And this isn't armchair speculation. A 2025 study imaged it directly, using seismic data gathered aboard a research vessel. The team found 2 active tears in the subducting slab and a fault network roughly 20 kilometers wide, cutting through sediment, through crust, and down into the upper mantle. The Explorer microplate is quite literally in the process of being severed from the system. Both of those magnitude 5.6 earthquakes happened inside that tearing structure, and that gives us the single most important line for interpreting them. These are fracture earthquakes on a plate that is coming apart. They are not megathrust earthquakes on the Cascadia interface. They tell us the northern end of the system is disintegrating right on schedule. They tell us nothing whatsoever about when the great locked zone will fail. There's one more thing about that Friday night worth a couple of minutes, because it breeds more suspicion than almost anything else in this field. For 20 to 30 minutes after the earthquake, the U.S. Geological Survey feed showed nothing at all. A European center published first near magnitude 5.6, with its standard note that the numbers hadn't yet been reviewed by a human. Earthquakes Canada initially didn't have it on the map, then posted it at 5.0. The European Center revised down to 5.3. And about half an hour after it happened, the USGS finally published at 5.6, with Canada eventually settling at 5.5. So the public watched the magnitude wander from 5.6 down to 5.0, up to 5.3, and back to 5.6 across 3 agencies in half an hour. And I know how that looks. It looks like a cover-up, but the real explanation is geometry, and it's boring in the best possible way. An earthquake 200 kilometers offshore has no instruments on the ocean side of it. Every station that records it is on land, all on one side. That one-sided coverage produces a poorly constrained solution. Depth in particular often isn't measured at all. It gets assigned a default value, and 10 kilometers is the classic default you'll see over and over on offshore quakes. The magnitude estimate then swings as more distant stations report in, and the automated algorithms settle. 3 agencies, 3 algorithms, 3 different networks, 3 different slices of the incoming data, and no human analyst yet. Of course they disagreed. The fact that they all converged within half an hour is the system working exactly as designed, not the system hiding something. There's a third thing happening on this coastline right now, and it's the one that genuinely connects the north end to the south end. Cascadia produces what are called slow earthquakes underneath the locked portion of the megathrust, the part that will eventually unleash a magnitude 9. The plate interface slides quietly over days and weeks instead of seconds, and seismologists track it as tremor. And tremor is not a countdown clock. It's a stress gauge. When tremor is running, the slab is being actively shoved beneath North America, and stress is being transferred onto the locked zone above it. Down at those depths, the rock is hot enough that it doesn't snap, it flows. So instead of storing stress until it fails all at once, the interface releases it in slow pulses that last for weeks and produce a faint continuous rumble rather than a sharp jolt. Nobody feels these. They were only discovered in the early 2000s, when researchers realized that the noise they'd been filtering out of their data was actually a signal. And every one of those slow pulses hands its stress upward to the shallower part of the fault that is still locked and still able to snap. Through the middle of July, that tremor was running hard, with more than 300 epicenters logged on a single day, climbing to nearly 400 by late July, with the concentration shifting toward the southern end, offshore Northern California and southern Oregon, and then it stopped. From late July onward, there was effectively nothing, just a small, isolated cluster and days of near silence. Now hold that against the primary story. The stated working relationship on this margin is that elevated tremor tends to come alongside what get called stress quakes in Northern California, the slab loading up and the strain expressing itself down the coast. And yet, tremor is currently at its quietest in weeks, and Northern California is producing a swarm anyway. That mismatch is a genuine puzzle, and it's exactly the kind of thing that keeps this from being a simple story. Which brings us to the big claim circulating online, the one that says all of this together represents the West Coast unzipping, a single connected failure racing down the plate boundary toward one giant California earthquake. The data does not support it, and the reasons are specific. The permanent stress change caused by one fault slipping falls off roughly as the cube of the distance from the source. The Vancouver Island epicenter is about 1,100 kilometers from Cloverdale. At that range, a magnitude 5.6 delivers a stress change smaller than what a passing weather system produces. The transient stress carried by seismic waves is real and has been documented at continental distances, but it's associated with much larger quakes, generally magnitude 7 and up, arriving at sites already teetering on the edge of failure. And the decisive fact is simply the calendar. The Cloverdale sequence was already running for several days before the Vancouver Island earthquake happened. The swarm did not start after that quake. It was already there. 3 unusual things are happening on the same coastline at once. That is not the same as one thing happening in 3 places. That distinction is the whole ballgame, and I'd love to know in the comments whether that surprises you, because a lot of what goes viral depends on people never learning that one simple fact. So here's what actually matters going forward. And this is the payoff I promised you at the start. On the Maacama, the thing to watch is not whether the swarm continues. Swarms continue. That's what makes them swarms. The thing to watch is whether the maximum magnitude climbs. The 20-20 sequence topped out at 4.2 and stayed there for 4 months. This one is currently at 4.2 as well. If that ceiling holds, the fracture mesh interpretation only gets stronger, and this becomes a fluid story that will run its course and quietly stop. But if a magnitude 5 appears, the interpretation changes, because that starts to look like a single structure taking over from the mesh. So watch the ceiling, not the count. That is the one number I promised would change everything. A 5? Watch the footprint too. If the sequence keeps spreading east to west across the grain, that's consistent with the mesh lighting up crossfaults. But if it suddenly organizes into a clean line along the Makama trend, something different is happening. At the northern end, expect more fracture earthquakes off Vancouver Island. A plate that is actively tearing apart produces earthquakes while it tears. A 3rd magnitude 5 in that same fracture boundary would not be a surprise, and it would not be a signal about Cascadia. It would simply be the Explorer plate continuing to do the thing it's been doing for ages. And on the interface itself, the number to watch is the tremor count. When the next slow slip episode begins, and it will, since these run on cycles of roughly 10 to 22 months depending on the segment, that's when stress starts loading the locked zone again. 326 years have now passed since Cascadia last ruptured, back on the 26th of January in the year 1700. Quiet does not mean the pressure has come off. It means the slab is simply between episodes, and so the single most useful takeaway in all of this is also the least dramatic one. A fault 75 miles north of San Francisco, one that scientists openly admit they don't understand well, has spent 6 weeks producing sequences that don't fit the standard model. That is not a warning of anything imminent. It's a reminder that a structure physically connected to the Hayward fault is being studied in real time by people who are refreshingly honest about the limits of what they know. There's something almost reassuring in that, isn't there? Not the false comfort of someone claiming to have all the answers, but the real, grounded honesty of scientists watching, measuring, and telling you plainly what they can and cannot yet see. The earth beneath Cloverdale is talking. We're finally learning enough to listen properly. And the ceiling, that one number, magnitude 5, is the word we're all waiting to hear, or hoping we don't. If this made the ground under your feet feel a little more understandable and a little less terrifying, then do me a favor and hit that like button, because it genuinely helps this kind of careful, no-hype science reach more people. Subscribe so you're here when the next update drops, because this story is far from over. And tell me down in the comments, do you want me to keep tracking this swarm day by day as it develops? I read every single one, and your questions often shape the next video. I'll see you in the next one.